Okay, hello everyone. I'm glad you're joining the class today. Um, okay, okay, let's wait for a few minutes. All right. Okay, let's check. Okay. Okay, let's start our course. Um, I think I already grade your quiz, right? So okay, that's I think some of you still let me check the quiz average. Okay, the average is 48. Okay, for the quiz. So okay, I think uh, yeah, around 48 to 50 the quiz. Half of the from all students you got below 50. Yeah, below 50. So I hope you get to improve. Need to improve for the next quiz. Okay, so after we finish the chapter of the polynomials, and also maybe get a new chapter about the I think the exponent and log. Uh, Maybe we will have a quiz. Okay, but let's say we just have to finish our polynomials first, and then we can have a quiz. Okay, and don't forget to submit your assignment. Okay, your assignment on Google Classroom. Uh, okay, and I think you already joined the Google Classroom, right? So okay, you can find the submissions there, and please submit the assignment. Okay, let's start our course. Okay, so first is let's review our feedback time. Um, the statement, if C is a real zero of polynomial P, then all other zeros of P are zeros of uh, the rational P of X over X minus C. So this is basically stated that if we have this, then the result of this division will have something, let's say QX. Okay, so all other zeros from this QX, there we have each zeros of some constant, right? Okay, because because P can be divided by PX. Okay, right? Okay, so this is just logical reasoning, and then that's okay from here. It's true, but then you have these questions. how many negative zeros polynomial px has. So negative 0 means, so when you have, like, for example, x minus 2, x plus 3, you have x equal 2, x equal negative 3. This is the negative zeros, okay? So from our case, or our polynomials here, we have 2x cubed minus x squared plus 4x minus 7. If you are looking here, let's just review a positive 0. Using the rules, the Descartes rules, okay, let me just review what this means. Descartes rule. If you look at this, you find that this is positive, this is negative, positive, negative. So positive to negative, there is one change, right? Negative to positive, there's two variation of signs, right? And then three variation of signs. So 3 times the signs is changing from positive, negative, positive, negative. Okay, so we have the possibility will be 3 positive 0, 3 positive zeros, or 1 positive zeros. It's always like that. Okay, so it will be always, if you have, for example, you have maybe 2. If 2, then 2 positive or 0 positive. If you have 1, it's only 1. Okay, that's the rule in the Descartes rule. You need to minus with the whole even number, which is the possible number that is oftenly used. It's just 2. Okay, if you have like maybe 4, then you have 2, you have 0. This is a possibility also, right? Okay, now the question is actually how many negative zeros. So negative zeros we can check with if we put negative x inside the polynomials. Okay. If you are going to check, then it will become negative, 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 and negative. So there is no changes. So it means that it will be 0. So there will be no negative zeros. All right. Okay. So how many negative 0 polynomial px? It's 0. Okay. Yes, it's possible 0. Okay. And no one answering correctly. So I will review a little bit about this Descartes rule before we move on in this chapter 3. And let's say we have questions. And feedback for quizzes or homework. Trigonometry part we will have maybe in 2 weeks later, I think, or maybe 2 or 3 weeks. Okay. The time is making difficult, of course. I feel some of the timers of the quiz too short. Yeah, I will prepare the time to be extended. Okay. But for the quiz, it's still have a timer, but I will adjust the timer to be extended, so you will have more time to calculate. But I cannot erase the time because I need the time to make sure that you are focused only on your quiz. Okay. Okay. Before we move on, let's review the Descartes rule and how to use Descartes rule. Okay. Okay. Let's say we have functions. Okay, that's the functions. Find possibilities on how many positive or negative zeros f of x have. And then the questions may be asking for find real zeros. Okay, just find real zeros. Okay. Okay, maybe this first for your practice. Okay, so don't forget to submit your assignment. Okay, so remember, assignment in this course. Okay, assignment, quiz, and then we have final. So we will only have these three, at least three major grading for basic math, aside from activity and attendance. Okay, we have three major grading. So assignment will be, I think uh, it's useful also for practicing all for your exam, and for your calculus also it's useful. And quiz will be, maybe we will have I plan for quiz, but maybe five or 4 or 5. Final, this will be uh, two types, two times final. The major will be just exam like usual, and the other one, like I think I mentioned sometimes in the early class, is like an oral test. But it's more like a video, like a video presentation. Okay. If you fail to submit assignment, we have assignment 1 already. You fail doing this, you fail doing the other two, the second one failed, the third one. I don't. I cannot help you to pass the course. Okay. No matter where you come from, I cannot help you for these cases here. Okay. Oh, we don't have midterm. We don't have midterm. We don't have midterm for basic of math, because if I put midterm, I think it's too much pressure for just a 0 credit course. Okay. Okay, let's go back to the course today. Okay, find possibility. One way to find possibility is we are using the Descartes rule. So Descartes rule. So let me write one more time. This is positive to negative. This is 1. And then this is second. So the idea will be 2 positive zeros or 0. And then for negative 0, let's check the negative x inside. It's negative x cubed, negative 2, x squared. It's become plus x plus 2. We will see that this is 1. So we will have 1 negative zeros, right? And like I said before, you can make a table, make it more clean, like positive, negative, imaginary. Remember, it can be possibility too. You have imaginary zeros and then the total. Because it's a polynomial degree 3, the total should be 3. Okay. Let's start from 2 and then 1 and then 0 and then 0 and then 1 and 2. Okay. Okay. If you're confused on how I can make sure that imaginary is 0 and or 2, this is because we know that the total should be 3. Okay. And the possibility of positive is 2 or 0. So positive has 2 possibility root, 2 or 0, right? And the negative is only having 1 negative 0. So it's only 1 and 1, right? Same 1. So 2 plus 1 is really 3. So there will be no imaginary zeros. So we have 2, 1, 0, 3, and then 0, 1, 2, 3. Okay? Okay. We have 2 possible roots. And then the questions is second question. So this is the first question. The second question is finding the real zeros. Let me write one more time the functions. Okay. To find the real zeros, first, I believe you can just trial and error if you want. But to narrow your number, we can check the factors. Check the factors. This is 2. This is 1. So factor of 2 divided by factor of 1. Or if you remember, we write this as P over Q. This is P, this is Q. Okay. Factor of 2 is 2 and 1. Factor of 1 is just plus minus 1. So this is plus minus, right? Okay, we can start with negative because we know that it may be having, and the fact is that it should be having 1 negative 0. So let's start with negative 1. So start with negative 1. So 1, 2. Okay, we get 0 now. So we'll have x plus 1, x squared minus 3x plus 2. This will be our functions. And then we can actually factor this out. This will be x minus 1, x minus 2. And yeah, we have this 3, this 3. So we have 1 negative zeros. And we have 2 positive zeros. And precisely from our possible root, we will have this as our answer, right? This is our answer. Okay, so in terms of polynomial, there are several methods that, or several ways that you can make of. You can start if it is asking directly how many real zeros, you can do directly doing this. Or if you want to make sure of the functions, you can make sure by doing this Descartes rule, make sure how many negative or positive they have, and then you can narrow the factor of the P and Q. For example, like this case, I'm focusing on the negative part because I know that it should be having a negative. Okay, but it's actually up to you which method you want to fine, and how the process is actually up to you. Okay, as long as the goal of that question is answered, or you have the solutions. Okay, any questions on the card rule? On the card rule. Okay, so I believe you are the familiar. Okay, familiar with the card rule. Okay, if not, then we can move on. Okay, and remember, if you have any trouble, like maybe the some of the part in the course, maybe the basic on calculus, or maybe some part in mathematics that you maybe still not really understand, especially in calculus. First, please consult consult with your TA first, okay, whether he can provide some maybe some suggestions to you. You can consult first to that TA, and if the TA says that maybe he's too busy, please let me know. Okay, I will maybe arrange what can we do for you, because I believe some of the concept, because it's really basic, it's really principles, we need more time to to understand, or to elaborate more. Okay, so one semester sometimes it's not really enough to got all of the chapters, all of the understanding. Okay, especially if you maybe a lot of things that you need to check, or to review. So we need to make sure that way. Okay. Um, okay. Okay, I think we can move to still in polynomials. I think we can move to the complex zeros and the fundamental theorem of the algebra. Okay, if there's no question here, let's move to here. So, okay, so this will be the fundamental theorem of the algebra. Let me move a bit up here. So we know that uh, with n, some n degree of polynomial, they can have at most n real zeros, right? Like I told you before, the total number of the zeros, it depends on the degree of the polynomials. Okay? And in the complex number, in complex number, the nth degree of polynomial has n zeros, and can be factored exactly n linear factors. Okay. And the fundamental theorem says that every polynomials with complex coefficients, so every polynomial px, this is the polynomial, okay, with n at least 1, okay, and the an at the beginning is not equal 0. Okay, so with complex coefficients has at least one complex zero. Okay, because any real number is also a complex number, we have talked about this a little bit in early class. The theorem applies to polynomials with real coefficients as well. So you can do this. Actually, what they say is, so the fundamental theorem of algebra and the factor theorem, they can show that polynomial can be factored completely into linear factors. Okay, so here's the theorem. If polynomials, the px is a polynomial of degree n, that n should be at least 1, then there exists complex numbers a, c1, c2 until cn, with a is not equal to 0, such that we can have this factorizations. Okay, so a complex numbers, this is a coefficient for a complex numbers. Okay, so a and c1, c2, and until cn. Okay, I think we can check using the example. Let's say we have px. Okay, so let's say we have px, okay, and then find zeros of p, find complete factorization of p. So 2 questions there. And then to factor it, okay, remember, okay, there are some way to factor this. Let me write some method to do that. First, we can try to use some division or synthetic method with some number that you probably can use from this p over q, finding the zeros. Or you can try to factorize. Okay. If you see the cube, okay, let me write here. So if you see this x cubed minus 3x squared plus x minus 3, you can check. For example, I will check x squared. This will be x minus 3. This is precisely x minus 3, right? And we can factor this and make it x minus 3 and then x squared plus 1, right? Okay. You can also factorize this. Sometimes you can try to doing something like this in polynomial. Try to factor out the x squared, factor out the x, factor out the, maybe x cubed if you have more degree. Check whether they have this kind of property. And if you have, then we can factorize easily. No need to check with p over q and then so on and so forth. But if you want to check with p over q, then you can only find the real zeros. And probably there will be some real zeros in this situation here. Let's say we have p over q. So we have factor of 3 divided by factor 1. So this will be plus minus 3 plus minus 1. Right? So we can check 3 or 1. And we can make sure which one we are going to follow. If we are looking here, this is 1 change here, 2 change here, 3 change here. So we will have 3 positive or 0, Or we can also check whether we have the negative. This will be negative x cubed, negative 3, x squared, and then minus x minus 3. There will be no negative 0. So we will have 3 or, oh, it's not 0. This should be 1, sorry. 3 or 1 positive 0. Okay. So we can check, for example, if you look here, the one that make 0 is 3. So it should be true that 3 is positive zeros, right? But here, we have px is x minus 3, x squared plus 1. So x is 3 and x squared is negative 1. This will be our complex, right? Our complex. So this means that the factor, or maybe not this one, sorry, should be the factor, this one. The factor is 0 when x equal negative plus minus. Okay, let me write plus minus I. And we can also write this using the complex and making px x minus 3, x plus 1 I, x minus I. So the zeros, 3, I, and negative I. So we have answered 2 questions from here. We find the zeros of P, and then we complete the factorizations. This is the complete factorizations for a polynomial P. Okay. Another way, if you find more complex in here, in a more complicated equations, you can check the quadratic formula directly to finding zeros, complex zeros. Okay. Okay. Any questions until here? Any questions? Okay. Okay. Please email me whenever you find a trouble, when you find difficulties, and any technical things. You can check with me. Okay. And the next thing here will be about the multiplicity. The multiplicity is actually not really that important, but this is just to show you that this I should include in the complete factorization. Okay. Complete factorization, what I mean is uh, this part here, we factor out the polynomials, right? And even though it has the complex, we can completely factor it out, making it this form here. We can make the complex into the factors that I called before. Is we complete factor the polynomials. Okay. Okay, now in this section, we are going to include the imaginary. Okay, the difference is that before, the imaginary is just, oh, it has maybe two or three, or maybe you can find also the imaginary, but not really writing into the complete factors. Okay, so sometimes it might happen in the polynomials. You can have the imaginary. Okay. Okay. Okay, I think we can go to the next part. Okay, what is multiplicity? Actually, this is should be on the previous sections, but I've skipped it because it's not too important. But let me just show you what the multiplicity means. Okay? So it means here, if I have p of x, this is x minus 1, 3 with power of 3, and then x plus 2 with power of 2, and x plus 3 with power of 5. This means the zeros is 1, -2, and -3. 1 has multiplicity of 3, or I will write m is 2, this is m is 5. So every polynomial that has at least degree 1, they have exactly n, some n zeros, and then it should be provided that a zero of multiplicity k is counted k times. So should be, for example, this cube. So it has the zeros, 1 is multiple 3 times. Okay, 1, 1, 1. Okay, but it's sometimes not really too much elaborations to make for the multiplicity. Let's just go to the conjugate zeros theorem. Okay. If the polynomial p has real coefficients, and if the complex number z is a zero of p, then its complex conjugate is also a zero of p. So usually whenever you have a plus pi, if this is, let me just write maybe completely here. So if a plus pi is this a complex, right? If this is a zero, then there will be a minus pi, which is the conjugate. This should be also zero. Okay, this is just saying that there will be a conjugate that also a zero of p. There are some equations to prove, but I think you don't really need that. Okay. Let me give you some an example on how we are going to use our conjugate. Find a polynomial p. of x of degree 3 that has integer coefficient and zeros. So you are getting in zeros information. Zeros is half and 3 minus I. So you have two zeros as your information. So you need to find, what you need to find is px is blah blah blah. So it should be x cubed something something, right? Okay, let me give you a few minutes to think and maybe try some value. The one who find the complex number, or the one who are using it for the first time, as the history setup is actually named Cardano. If you want to find the name who find the complex, its name is Cardano, on 1501, born 1501, and this is on 1576. This is when he died. So this is the one figure that finding the complex number. Oh, Jordan, you want to ask this? Okay, sorry. Let me go back through here. This one? Okay, check here. See this, the red circle? Take out x squared. Okay, that's where it's come from. So sometimes you can factor out using this way, or you can factor maybe x cubed, or x squared, and then factor out, and you can have this nicely x minus 3. And then from this x minus 3, factor out x minus 3, come here, and this will be easily factorized. Okay, got it? Okay, that's where it's come from. X squared plus 1. Okay, let me erase. X squared plus 1 is, you have this you have this one, right? Then you factor out x minus 3. Factor out x minus 3. So factor out x minus 3, or let me write one more time. Okay, you got this, right? Factor out x minus 3. So x minus 3 here, x minus 3 here. Okay? X minus 3. And then this is x squared. This is plus 1, right? So this will be x squared plus 1. If we check, x minus 3 check with x squared, it's become this one, the left one. X minus 3 check with 1, multiply with 1, this will be the results. Okay. Or if you are maybe not sure why it's correct, we can make sure to check. Okay, so x cubed minus 3x squared, check with that, minus x plus 3. Oh, we are done that. This is our complete functions, right? Okay. Okay. Okay, now back to this question. So it's asking what polynomial we will have, right? So first, let me maybe using blue color. So first, we know that 3 minus I is a 0. Because this 3 minus I is 0, I will have another conjugate that 3 plus I should be 0, right? According to what the theorem says, that the conjugate theorem. So first, our zeros is half, so I will write x minus half, okay? And then I will write x minus 3 minus 1 for the first one here. And then the second one, x minus 3 plus I. And then let's try to simplify and then expand and multiply each factors. And I need to write some coefficient on at the front here. Let's say a. Okay. Because we want to make at the end of the process, we want to make sure that all the things inside all need to be integer. So you need to remember the questions. It needs to be integer, right? So it needed to be integer coefficients. Okay. So coefficient should be integer. That's why I need to take some, or to put a, to make sure that at the end of the process I can multiply with something a. We can set a with any number later, and then make it all to be integer. Okay, let's write this is px, right? Okay, let's start slowly. Let's start to first, maybe this will be x minus 3 plus I, okay? Because I know that there will be 2x minus 3 here. I will make a bracket here, okay? Start slowly, x minus 3 minus I. And then I will make a bracket here. Okay. This is if you have a plus b, a minus b. If you multiply, this should be a squared minus b squared. Okay. Then we can do that. We can apply those a squared minus b squared here, and setting up with x minus 3 becomes x minus 3 squared, and then minus I squared. Okay. I squared, it's become 1, right? Or become negative 1, right? So we can expand this. Maybe I can write here x squared minus 6x plus 9. And then this is minus minus it will be plus 1, so it's plus 1. So I can write here x squared minus 6x plus 10. And then let's multiply one by one. So multiply all here, x cubed, and then minus half x squared, and then minus 6x squared, or let me write one by one. Plus 3x plus 10x minus 5. This will be 13 over 2. Okay. And then because of this, we have a fraction. Then we can set up set a equal to remove 2, right? Remove this 13 over 2. So set a equal to, so we will have bx is 2x cubed minus 13x squared plus 26x minus 10. Then this will be our solutions. At least one polynomial that satisfy the requirements. Okay, any questions? Any questions? Imaginary number. Okay, let's start with the imaginary number is this. Wait, right? If you have I squared, it will be -1. Okay, and then this is negative, -1, plus 1, right? Okay, you get it? Okay. Okay, now we can move to let's say the linear and quadratic factors. Okay, let's move. Okay, let's move that way. Okay, linear and quadratic factors. Every polynomial with real coefficients can be factored into a product of linear and irreducible quadratic factors with real coefficients. So there is another term here we called irreducible factors. This in terms of real zeros. Okay, so for example, if you have px, you have x with power of 4 plus 2x squared minus 8. The question is factor p into linear and irreducible factors with real coefficient. And the second one is factor p completely with complex. The irreducible factors is, I believe, something that you will hear in the calculus, maybe in chapter 4, when we learn about graphing the functions, you will hear the terms irreducible factors. So irreducible factors is, in terms of real zeros, is something that you cannot factor out anymore. For example, this case here, okay, this px here, let me write here. Let me write one more time here. Let's just find the factors. Okay. How to find the factors? First, okay, let's say we have a is x squared. Let me check this one. So if I have a is x squared, then I have a squared plus 2a minus 8. This way I can factor out, right? So I will have a plus 4 and a minus 2, right? And a can be -4, a can be 2. But let's say we stop at these factors. Okay, let's turn back to the x squared. Okay, so p of x will be x squared plus 4 and x squared minus 2. This one here, the x squared minus 2, we can factor out and make it plus square root of 2 minus square root of 2, and then this is still x squared plus 4. And if you look at this x squared plus 4, because it has a complex later on, we are looking at it has a complex zeros. So we cannot factor it out in terms of real. Okay, so in terms of real, we call this irreducible factors. So it will stay as it is. Okay, it has a complex, but in terms of real numbers, we cannot do anything for these factors. Okay, that's why it's called irreducible factors. We cannot reduce in any way, right? And to get the complete factorizations in complex, we know that the x squared plus 4, this will be equal to -4. So x will be plus minus 2i, right? Because it will be, x will be or directly write this is 2, or this is 2i plus minus. So we can write the factors as x plus square root of 2, x minus square root of 2, and then x minus 2i, x plus 2i. Now this is the complete one. We are including the complex. Okay. Okay, any questions? Okay, if not, let's continue. We are going to move to other sections still in polynomial. We are going to move to the other sections. This is about the rational functions, asymptotes of rational functions, the slant asymptote. I will give you the definition of a slant asymptote. So this will be a rational function. So we are going to have rational function as p over q. as we maybe mentioned earlier in the polynomial. Okay, so P and Q are polynomials. Assume P and Q have no other common factors. And first, let's start with the f of x. The easiest one is 1 over x. Okay, now I think I also doing the same approach in the calculus, in the limit, right? If you remember, when we are dealing with this, when we have x maybe getting closer to 0, maybe 0.1 and then 0.001, or maybe 0.000001, right? The functions is getting bigger, right? When you are dealing with the more 0, right? And you can also check when you are doing with the -1, nearby 0, closer 0. Check the negative zeros and you will see it will be getting bigger, but it's negative, right? Negative bigger. So negatively large. Or we can say that we can see that this is approaching infinity, this is approaching negative infinity. Okay? If you check from the table also. If you see the graph, I think maybe something like that. Yeah, maybe something like that. Okay, probably. So x going from approaching 0 from the left, f of x is getting negative infinity. As x approaching 0 from the right, f of x is getting positive infinity. Right? Okay. This is a little bit review also for your calculus, and hopefully it can be useful as well. And the domain will be all x except at x equals 0. Because if you remember the limit, this is going up, this is going down. At 0, you can have definitive value, right? And remember, when we are doing this is actually creating a line here. A line that the graph will never touch. Okay? Will never touch. At least it seems never touch. But there will be some asymptote that it's not that similar with this asymptote. There is another asymptote that maybe the graph can cross the asymptote. It can be. It can be. I will explain later on. For example, something like this. This graph will be like this, and it's going like that. Yeah, maybe like that. So from here, the line will it will never touch 0. So you will have asymptote here. But actually, if you are elongated the line, it will cross here, right? But it's okay because it's one side. You will have some like the graph never touched the asymptote. So it might happen in some cases of functions. So it can be uh, crossing the asymptote might cross the function as well. So it's okay. Okay. So from here, we can get some definitions on the asymptote, at least the vertical asymptote, and later the horizontal asymptote. Okay, we can check the definition first. Okay, so we will have this x equal a as a vertical asymptote. Okay, when you look here, as the x approaching a from right, it's going up bigger. Also, as x approaching a from left, it's also getting bigger. And it's also, we can see this, the other case that is going down, getting negatively large or negative infinity. And we have also the horizontal asymptote that has, uh, the difference is when we are approaching b, so we are uh, looking at the x now is getting infinitely large. So x is getting large, and it's getting somewhere on this b. It's closer to this b. Okay? And we can say that we can have y equal b is our horizontal asymptote. And similarly, we can have this as our asymptote as well, y equal b, when you have, when x is getting bigger to the left, getting negatively large, our y is also getting to have some finite value at b. And this is what I called before. It might happen that the asymptote crossing with the graph, or the graph is crossing the asymptote. That can happen too. But I believe it won't be happen on vertical asymptote. It might be happen on horizontal asymptote, or maybe the slant asymptote. It might happen. Okay. Any questions? No? If no, then we can uh, try the other section here. This is graphing rational functions. Okay, one way to graph is we can use the transformations. If you remember the graph early from the previous slides, we are using the functions of x that is 1 over x. Okay. Now, if we look here, the rational functions for r and s, I believe we can make it into 1 over x, right? For example, this case here for r, Rx is 2 over x minus 3. We can take out 2, and this will be 1 over x minus 3. And what this does is, this is actually f x minus 3, right? So if you have f x minus 3, this will be 1 over x minus 3. And then you need to multiply by 2, and then this becomes the Rx. So this is one way, okay, one way to imagine any functions that you might have in calculus. You can use transformations. Okay, you can use transformations. Okay, is it helping for you? Is it helpful? I think it is helpful because you can easily imagine the curve. Okay, now the graph. Okay, if we try to graph, we can look at this one. Okay, let's see here. The graph. We have the red curve here, which is actually similar with our 1 over x. 1 over x we have initially here, right? Initially here. And then we are moving that to the right 3 units. So 1, 2, 3. This will be our center. And then we multiply with 2. So that's why if we have this maybe 5, this will be equaling 1. Okay, right? So we are multiplying by 2, shifting to the right 3 times, and multiply by 2. So let me write here. R is obtained by shifting F 3 units to right and stretching vertically by a factor of 2. So if the question is asking 1 over x something in the question, and you want to the question want you to describe how the functions transform, this is what you can write. So shifting and then stretching, okay, and it has the vertical asymptote x equal 3, as you may see from here. When x equal 3, Rx will be going to have infinity, right? Or negative infinity, depends on which part you are in. Okay. If you are confused on deciding positive or negative, you can check like this. Okay. X is close to 3, so you can check 2.9 and check 3.9. The one give you positive, the one give you a negative, right? So from here you get to know that at around here it should be going negative infinity, and this should be going positive infinity. Okay. That's how you check. And then another one here, y equals 0. For this asymptote, this will be x getting bigger. And what will happen with the y or the Rx? It's getting closer to 0, right? If you have 2 and then something big here, something big or infinite, this will be 0, right? Same way, if you look at the left side here, it's also getting to 0. So should be having an asymptote of y equals 0. Okay, we are having another questions, right? This one here. Okay, what we can do from this S, first, let me move here and then first write the 3x plus 5, x plus 2. First, we just use our long division. This is 3x plus 6, and we get this is negative 1. So we will have 3 minus 1 x plus 2, right? Okay, now what we can do from here using transformations, remember our f of x is 1 over x. Then if we move this to the front, then we can say that this is actually our negative f x plus 2 and then plus 3. Okay, I hope you get beneficial from this. And we can arrange this and make it into something like this. Let me get close here. So first is remember the 1 over x. 1 over x is here, the original functions. Maybe we can mirror first and make becomes like this, the green one, right? And then we can move to the left first and becoming this negative 2 here, and then move upwards to this 3 units here. So this will be the center, right? And then let me clean all of that. And then here we have the graph. Okay, of course, if you see the equation here, you will notice that you will have this x equal negative 2 that makes the equations undefined. Precisely, that is our vertical asymptote. Okay, and our y equal 3 will be the horizontal asymptote. Why? Because if you look here, when x is getting infinity, when x is getting bigger, the whole thing here, the left one will be 0, and it's just 3. So y equal 3 is, of course, the horizontal asymptote. Okay. Okay, do you get it, or do you want to review a little bit more? Any questions? Okay. Let me give you an example on how we can also drawing a graph. Okay, drawing a graph. Okay. It's the section is called asymptotes of rational functions. let's say you need to graph this. So graph Rx. So first, we can look at this function. Let me write the top equation as it is. And the bottom one here, we can actually factors, right? That's our factors. So we can write x minus 1 and then squared. And we know that x equal 1 will be our vertical asymptote. Okay. This is similar with the calculus part, except it's not using any limit at all. And then we can have the expressions. And similar with limit, when we have this, you know that it has the same degree too. So let's try to multiply with 1 over x squared, 1 over x squared. This will be 2 minus 4 over x plus 5 over x squared. 1, 2 over x plus 1 over x squared. In limit, you can get the idea that this will be 0, right? But here, we just use our logical reasoning. When x is getting bigger, then we can say that y equal to when x is getting infinite or negative infinite, y will be 0. So y equal to will be horizontal asymptote. So at least you can draw, and maybe make sure this will be 1. This will be vertical asymptote. This will be 2. This will be 0. This will be 1, 2, and then this is another asymptote. And probably here is your function will be. Why it's 2 is from here. Okay. As the x getting bigger or getting negative infinity, you will notice that when you have 4 divided by infinity, it will getting closer to 0. So it means that if this is 0, this is 0, and this is 0, and this is 0, y will be equal to, right? It's not quite 0, actually. We can say it's getting closer to 0. It's getting closer to 0, or we can say that it's never touched 0. But we can just assume that way, so that in the asymptote here, it will be not getting any touching here. So this should be, yeah. Okay. Okay. Some theorem I can give to you is that if you have irrational functions R, this theorem say that the x equal a will be the vertical asymptote, where a will be the 0 of the denominator. So that is actually we have done, and that's true. And then if n is less than m, where's n and m here? The degree, you can see the degree. Then you will have asymptote y equals 0, right? Because the bottom one is bigger, right? And if n equal m, then you have this a over b. It's actually what we have done here. So whenever you see here, because it's actually the same. We can say directly without any calculation, okay, y equal to is the horizontal asymptote. Okay. The way to prove it, we can just check with this divide by x squared, the biggest degree of the polynomials, and that way we can see that it's actually y equal to. Okay. And if n is larger than m, there will be no horizontal asymptote. I think that is actually quite reasonable. Okay. I will go to the common factors. If you have as x, if you look here, we can write this as x minus 3, right? And actually we can write this as 1 over x, but x is not equal to 3. We can write like this, right? Okay. It's this, so it means that Sx is the same or similar with, it's the same with the with functions 1 over x, but or except it has a hole. So it's different. Okay? It has a hole at x equals 3. So if I were asked, maybe you are dealing with this, and then you say that, oh, when x is equal to 3, the denominator is 0. And you notice that, oh, then x equal 3 will be a vertical asymptote. And this is wrong. Okay, this is wrong. If this happen, it's called the common factors happen. It's this and this. It's actually not something over 0, but this is 0 over 0. So when this happen, you cannot confirm or you cannot conclude that it's a vertical asymptote. Okay. Instead, it is a hole. All right. So maybe the graph will be the same as the 1 over x. And if you try to draw in the GeoGebra or any website, it will show you the same graph with 1 over x. But when you're going closer and closer, maybe around here, this is maybe 3, you will notice that there was something wrong with the graph at this point here. There will be a hole here. So there will be a hole at x equal 3. This should be helpful for your calculus. Okay. Okay. Lastly, is the slant asymptote. Okay, slant asymptote. Okay, if Rx are Px over Qx, if this is a rational function, degree of numerator or Px numerator is one more degree of denominator. Then we can express this in terms of, there will be some ax plus b, and then plus the remainder, and then the quotient over quotients. Okay. Now this is called the slant asymptote. Okay. For example, if you have Rx, this is example. equal x squared minus 4x minus 5 divided by x minus 3. We can factor it out. And let's say we have x plus 1, x minus 5, and x minus 3. We can find, if you want to graph this, we can find the horizontal asymptote, we can find the vertical asymptote, right? And then, because this is degree 2 and this is degree 1, there should be a slant asymptote that is this as ax plus b. If we are going to check, then we can check with the long division. Minus 5 minus 8. So we will have Rx is x minus 1 minus 8 x minus 3. So this will be our slant asymptote, y equal x minus 1. And this will be y equal x minus 1. And this will be the line. Okay. And again, we have an asymptote that is not vertical, not horizontal, but it has some slope. Okay, it has a slope. Okay, it has some certain degree of slope. And remember that whenever you find this at least 1 degree more than the bottom one, the denominator, then you can have those slant asymptote. Okay. So probably tomorrow I will take some time to review again for this whole thing here, because I think you need to have some at least 2 or 3 more examples to make sure that you're already familiar with all the terms and all the graphing things. Okay, because in your calculus part, in your class, in calculus class, you will learn in chapter 4 about all of this, finding the asymptote, a slant asymptote, and also related to the calculus part is the slope, the first derivative, second derivative. You will learn all of that in calculus. So probably it's best to have a good foundation on basic of math for those graphing functions. Okay. Any questions? Any questions? So have another asymptote aside from horizontal, vertical. There is a slant asymptote. And I haven't shown you how to at least getting more information from the functions and then turn into the graph. Like for example, you need to find this intercept, uh, like this one. You need to find that one as well. And probably if we have a quiz involving any graphing like this, I will not include drawing a graph. So maybe just like give you some options to choose. As long as you know how, then I think that should be fine. And maybe the graphing things will be maybe in the if we have a physical exam later, if you guys already in Taiwan. Okay. Okay. If there's no questions, um, any questions so far? Um, how's your because we just have the first quiz last week. What do you guys think of the questions for the quiz? Uh, is it just the time that is making the all the aspect maybe a little bit difficult for you, or is it, how about the question itself? Is it too difficult, uh, or okay quiz? What do you guys think of the quiz? It's fine. Okay. But I think I need to adjust the time. Okay, I need to just adjust the time so that you can have more time to think and do some calculations. Okay. Any other feedback about the quiz? While I'm checking the wait. Okay, maybe a reminder for you. We have, I think I've been present at the beginning of the class that our activity score will be around 20%, quiz will be 50%, final will be 30%. We have activity. This include the assignment, your small quiz every attendance. So attendance also here, and quiz because it's 50. Actually, I'm preparing 5, but let's see how we can deal with this. So the first quiz we already done. The first quiz is about the fundamentals and functions, right? The second quiz probably about the polynomials, all about the polynomials. And the next chapter will be, there will be an exponent and logarithm after this one, and there will be trigonometry. The other one, we will have a polar uh, polar coordinate conic section, as I remember. Okay. Um, and then series and sequence, but probably I will drop one of this section if we are, maybe if I think it's too difficult to adjust in one semester, maybe I will adjust the chapters. But this is what usually we are doing in the previous our last year basic of math. Okay, that is the chapters. And for final, uh, actually I'm preparing like the really exam, physical exam, but probably this will be less percentage, maybe 15, or 15 is equal, maybe 10 to 15, or maybe 15. And the last one here, the video part, this you need to make, uh, or oral, this you need to make more points here. Okay, I believe you need to get more point in video or oral. Okay, so making some video of basic of math, but the topics is still in I still need to find suitable topics. Okay, if there's no questions, let me go through the notes. Oh yeah, I will share the note. Okay, thank you uh for the reminder, Ardian. Okay, I will share the note. I think I forgot to share the chapter 1 and chapter 2, the first one, the first note. So I will share chapter 1 until 3 for you to check and then to review. Okay. So I think chapter 3, actually we finished chapter 3, I believe. There is actually one more sections that I think maybe we can solve tomorrow. So tomorrow we'll be finishing the chapter 3 and maybe moving to chapter 4. So probably next week or next 2 weeks, I will announce like the duration of the quiz and maybe where you can find the link. You need to join the Google Classroom first, and then you can check the link for the quiz. Okay, I think most of you already joined the Google Classroom. Which one? Which students who are not joining? Uh, you need to check the Moodle on how to join the Google Classroom. I won't tell you any more things how to join. I already repeated many times in class. It's your fault if you are missing the class. I already put in the Moodle every time I check with you, always in the Moodle several times, like join the Google Classroom, join the Google Classroom. Okay. If you're not joining, it's your fault. Okay. And if you're not passing the course, it's also your fault. Okay. I already mentioned many times for joining the Google Classroom. I think most of you are already joining, and that's good. And we can have our course ongoing. Okay. Now, the final part on our course today is, of course, the feedback time. And okay, so actually this is about rational function. So uh, please check, and hopefully you still remember the last part of our lecture today. So I'm not including the previous part about the Descartes rule or the before that. Hopefully or the complex here. So this is focused solely only the rational function. I hope you remember. Okay. 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 So I will share the notes after we finish the chapter 3 tomorrow. I will share the chapter 1, 2, 3 into one PDF folder, and you can review. Okay, let's wait for a moment. 5 students. Okay, let's just get through. Let's start with the first one. I hope I already adjusted time. If not, I will rearrange. Okay, like 3, 2, 1. Let's start. Yeah, I hope that's enough. 1 minute, 1 minute half. 1 minute half. Yeah. And hopefully the basic math benefits for you, for especially for calculus. Okay. Okay, we have 35, 34. Okay, 30 seconds. 10, 9, 5, 4, 3. Okay, just random answer, random answer. Okay. Okay, I need to review that part. Okay. Okay, next question. Or let's see who get correct. Okay, good, good, good. Okay, good. Okay. Get ready. 3, 2, 1. Let's start. Yeah, I believe you can do faster. You can do faster. I think you can do it in below 10 minutes, I think, right? I'm just giving you more to have some time to think and avoid mistake, right? 50. Okay. Okay, 12, 11, 10, 3, 2, 1. Okay, now good. Okay, now it's good. Okay. Okay, good. Scarlett for winning the game. Okay, I will collect all your trophy and then see who are getting the gift. Okay, so whenever you come to Taiwan and when you have a physical exam, I will present the gift for you. Okay, okay, congratulations, and that will be the last of our uh, lecture today. So thank you again for coming, and I hope you get benefits from my lecture today. And I will review a little part of what we have done today tomorrow. And I think we finished the chapter 3 tomorrow. Only one more sections to go. And see you next. Oh, see you tomorrow. Yeah, see you tomorrow. We will still have one more lecture tomorrow. So you can leave the Google Meet if you want. Okay. Yeah. Yeah. Thank you. Thank you. Thank you for coming too. Okay.